examine it, and maybe we could detect that this particular series diverges or maybe it converges. And this investigation is carried out by comparing the given series you're looking at, which in the statement of these theorems is the series sum of AM. You're comparing that, as the name suggests, to a series that you know about. Okay? Now, typical examples that we looked at last time was where the comparison series we were using was one of the hypergeometric series. The hypergeometric series is any series of this form down here. The sum of m, as n goes from 1 to infinity, of 1 over n to the p, for some fixed power p. And we with the aid of the integral test, we completely know about the convergence of these hyperharmonic series. They converge for p strictly greater than 1, and they diverge for p less than or equal to 1. So any function, any series whose terms are defined by a ratio of polynomials in the index, those normally are susceptible to using the comparison test and comparing it to a hyperharmonic series. In the examples we looked at, we took the overall behavior of the series we were investigating. So we looked at the highest power of the index in the numerator and the highest power of the index in the denominator, and when we looked at the difference of those powers, and that told us which hyperharmonic series to use for the comparison. But they can also be used in other situations as well. So there's a few more tests to look at. So we're going to talk through some of these now. I won't give detailed proofs for them, but I'll give kind of suggestive arguments or motivations for why they're true. And then we'll have a look at some examples of their application. Okay? So remember, the way to think about these convergence tests, or one way to think about them, is it's like a toolbox, a collection of tools, collection of tests, which, given any particular series that you want to find out about, whether it's a divergent series or a convergent series, you select one of the tools from the bag and you examine the series with that tool, and it may or may not give you a conclusion. And sometimes it's a kind of process of trial and error, but as you do more examples, you get more used to noticing the types of series that each particular tool is appropriate to. So those comparison tests we just looked at, those will generally work on any series whose terms is a ratio of polynomials in the summation index. Okay, so let's look at the next one, theorem 2.8, which is the alternating series test. So as its name suggests, this applies to so-called alternating series. And an alternating series is one whose terms are alternatively positive and negative. So you have a positive term followed by a negative term, followed by a positive term, followed by a negative term, etc. Okay? Now that is normally observable in the formula for the term of the series because of the presence of minus 1 to the power of well, in here it's written to the power of m, although the index there, the power on the minus 1 could be some other kind of function, some other kind of simple function of the summation index. So in this statement of the test, the AM terms are, we're assuming that they're all positive. So the terms of the series then will be alternatively positive and negative, okay? Because that minus 1 to the power of m produces an alternating positive and negative sign. Negative for m equals 1, positive for m equals 2, negative for m equals 3, and so on. Okay? So we'll assume that the AMs are all positive and that they are decreasing. But now you'll notice that there's a misprint there. So we're assuming the AMs are decreasing. Now I've written the inequality the wrong way around there, haven't I? Because it should be that AM is bigger than or equal to AM plus 1. So maybe you could make that correction there. So you have to reverse this inequality here. So the AM should be bigger than or equal to AM plus 1. I'll correct that in the notes. Well, the conclusion of this test is that if the terms, additionally, if the terms are converging to zero, then the series is convergent. If the terms are not converging to zero, then the series is divergent. Okay. Now this is fairly easy to appreciate why this might be true. So the way to think about it, or the motivation for the proof or the explanation of why it's true, is that we think of the partial sums as stepping up and stepping down. Now, what do I mean by that? Well, see, each term in the series is alternatively positive and negative. So if you're looking at any particular partial sum, remember the partial sum of the series is the sum of some amount of the initial terms of the series. Well, let's say the next term you're adding on is one of the positive ones. Well, that's going to slightly increase the partial sum. The partial sum is stepping up. But then, because it's an alternating series, the next term you're adding on is a negative term. So that's going to slightly decrease the new partial sum. So you step down. And then you step up again, and then you step down. Okay? Okay, since the terms of the series are alternating. So if, in addition, the AM are converging to zero as m goes to infinity, then you can kind of draw a suggestive kind of graph of how the partial sums will evolve as k increases. So the first partial sum is going to be somewhere, then it's going to increase with the second one, then it's going to decrease. But you see, because the step size that's added on to each partial sum is the next term in the series. They're alternating, so you're stepping up and down. But in addition, from the conditions of the theorem, the step sizes are converging to zero. So you can kind of observe or kind of appreciate or get the feel that the partial sums are going to have to be zeroing in, if you like, or converging to some limiting quantity. Okay? So this is k equals 1, k equals 2, k equals 3, k equals 4, k equals 5, etc. Okay. So we observe the convergent behavior. I mean, it's not a strict proof by any means, but just a kind of suggestive argument. We observe the convergent behavior of the partial sums. So if the sequence of partial sums is converging, by definition, then the series converges. So the series, which is the sum of minus 1 to the m am, m goes from 1 to infinity, is convergent. And if the step size isn't converging to zero, if the terms, the absolute value of the terms isn't converging to zero, then the series won't be convergent, because the partial sums won't be converging as a sequence. Okay? Partial sums will be kind of still changing by large amounts, or changing by amounts that aren't converging to zero. Okay? So considering this picture, when the AMs do not converge to zero, suggests why the series, the alternating series there, diverges in this case. That's when the step size is not converging to zero. So when I do the arrow 0, that will be converging to 0, but when I strike it through, it means it's not converging to 0. Now I'm just going to run through the next couple of tests, and then we'll turn to do some examples and look at some examples of their application. Do interrupt me anytime if you've got any questions or points you'd like clarified or anything. So the next test to look at is the ratio test. So we'll get that up on the screen again. The ratio test. The ratio test, as its name suggests, this proceeds by examining the ratio of successive terms of the series. Oops, sorry. Okay. So whatever series you're examining, again, it's represented here as the sum of AM. The series you're examining, what you look at is you form this ratio of successive terms, AM plus 1 divided by AN. So that ratio there we're looking at is one term of the series divided by the one that came before it. Okay? And what we do is we examine that ratio, that sequence of ratios. So we take the limit of it as n goes to infinity. Okay? So you're looking at how one term in the series compares to, relatively the term that came before it. That's what the ratio expresses. And how that relationship evolves as you look out along the series. When you take the limit of that as n goes to infinity. If that relative relationship between successive terms, i.e. the ratio, if that ratio is a convergent sequence and converges to a limit, then we'll probably be able to draw a conclusion about the series. So the conclusion is based on considering the value of the limit L. If L lies between 0 and 1, remember there's the additional consideration here that the terms of the series are all positive. If the limit L lies between 0 and 1, the limit has to be bigger than or equal to 0, because everything's positive. If the limit is between 0 and 1, strictly less than 1, then the conclusion is that the series converges. If L is strictly greater than 1, you get the negative conclusion that the series diverges. And the one remaining case, if L is exactly equal to 1, then it's a little bit you can't draw the conclusion. Okay, the series could be converging or it could be diverging. Okay. Now there's a bit of an explanation we can give for that. So the ratio test can be proved by comparing the behavior. So it would be using a comparison test by comparing the behavior of the series we're looking at with a geometric series. Now what do I mean by that? Well, you see, if the limit of these ratios, if the limit is equal to L, okay, what that means is then now this is a little bit vague, but for large n, you wait around long enough, if you look far enough out along the series, you'll see that AM plus 1 is approximately, well, the ratio is, let's just say, approximately L, because it's converging to L. So we can make the ratio get as close to L as we want by just waiting around long enough, okay, because the ratio is converging to L. But then that will mean that am plus 1 is approximately L times am. Yeah, just multiplying both sides of the approximation by am. So that will mean that if you wait around long enough for large enough m, you look far enough out along the series, each term in the series is approximately L times the previous term. Now that's the behavior of a geometric series. The behavior of a let's say it's approximately the behavior of a geometric series. Geometric series behave exactly like this. For each term in the geometric series is exactly some fixed ratio, we called it R in the case of a geometric series, but some fixed multiple of the previous term. Okay? But if the ratio test gives you this limit L, it means the series you're looking at is behaving approximately like a geometric series. Okay? And so, if L is strictly less than 1, then the corresponding geometric series will be a convergent one. Okay, so that will be using a comparison test. So if the corresponding geometric series, the geometric series with this fixed ratio L, that geometric series will converge, and so by comparison, so will the series we're looking at, sum of AM. And similarly, if the L is strictly bigger than 1, then the corresponding geometric series will diverge. Because remember, the geometric series test says that if the R, well, we called it R in the geometric series test, but if that ratio R is strictly bigger than 1, then your geometric series is divergent. So in the same way, by using the comparison test, we'll then be able to conclude that the series we're looking at here, the one which has this behavior here, this one will diverge, just like the corresponding geometric series. So this is a nice illustration of how these convergence tests can link together and be combined to produce new results. Okay? So using the geometric series and the comparison test, we can construct a new test called the ratio test. So the ratio test detects when a series is behaving approximately like a geometric series. And if it behaves approximately like a geometric series, then if that geometric series converges, so will the series we're looking at. If the geometric series diverges, then so will the series we're looking at. Okay. And we'll see some examples shortly, but situations where you use the ratio test are situations where you're able to determine this limit here. So if it's possible to determine what this limit is, and I'll give you some pointers on when it is shortly. But when this ratio of successive terms simplifies enough, or is when you can understand it sufficiently to determine the limit of it, then you'll be able to apply the test, because you can evaluate the limit and compare it to 1. Okay. We'll see some examples of that very shortly. But before that, we'll just look at theorem 2.10, which is very similar to this in that it has the same motivation, the same explanation. And that's the root test. This is the root test. Now it looks kind of curious, kind of funny, and it's only really applicable in certain situations. But the way it proceeds is, again, you're examining a series, the sum of AM. You're trying to find out whether that is convergent or divergent. And the way it proceeds is you take the nth root of the nth term. So we're looking at AM to the power 1 over n. Okay, so that's the nth root of the nth term. And again, we're taking the limit of that. If it's possible to find out what that limit is, it's possible to evaluate that limit to find out the number L, then we can make a conclusion, or then we may be able to make a conclusion about the convergence or divergence of this series. And it proceeds just like in the ratio test. If the limit L is strictly less than 1, it's convergent. If the limit L is strictly greater than 1, it's divergent. And again, the explanation for this is pretty much the same as the previous one. Okay. So theorem 2.10. If the limit as m goes to infinity of am to the power 1 over m is equal to L, then, you know, for large enough n, so these explanations are kind of vague because to prove them precisely, I'd have to get down to the epsilon arguments and talk about, you know, if someone asks for a specific degree of closeness to the limit, I wait around this long and then do the comparison test with the resulting inequalities that come out. But we'll content ourselves with this for the moment. For large enough m, am to the power 1 over m is approximately L. And that's going to imply that the am term is approximately L to the power m. Okay. Now, L to the power m, as m increases, those are the terms from a geometric series. You're adding up successive powers of a fixed quantity. Okay, that's a geometric series. The terms from a geometric series. So, if L is strictly less than 1, then the sum of L to the power of m converges. So by comparison, because the AMs are, you know, converging to this in a sense, so by comparison, so will the sum of R terms, the sum of AM. And if L is strictly bigger than 1, it's the divergent behavior. If L is strictly bigger than 1, then the sum of L to the power m, it diverges. So by comparison, and I'm really just repeating myself, so by comparison, so will the series under investigation. So by combining the comparison test and the geometric series tests, we can formulate two kind of related tests, this ratio test and the root test. And again, now we'll see some examples, but you know, where might you apply, or where might you try and apply the root test? Well, you'll only be able to apply it if you're able to do this step, if you're able to evaluate the limit of the nth root of the nth term of the series. Okay. If you can evaluate it to some number, then based on whether the number is bigger than or less than 1, you can draw the conclusion. And both the ratio test and the root test have this feature that if the limit comes out as exactly 1, then you're a bit stymied. It could be convergent, it could be divergent. The test is inconclusive. Okay? So in both 2.9 and 2.10, the ratio test and the root test, if the limit L is equal to 1, then no conclusion. No conclusion is forthcoming. If you want to determine the behavior of the series, you'll have to try other methods. Or maybe get down to a very close and careful epsilon argument, looking at the terms of the series. Okay. Okay, so I've got a bunch of examples here. So I think the thing to do will be to jump into those, and yeah, we'll see the application of some of these tests. Okay. Is that okay? Is everybody got that page? Okay. So let's see some examples. So for the first example, we'll consider this particular series. So if the sum from m equals 1 to infinity of 2 over n to the power n. Sorry, 2 to the power 2n over n to the power n. Now, I mean, this, in some ways, this kind of feels like an artificial example. You can see the terms of that series. There's a lot of raising to the power n going on. Sorry, these are n. Sorry. Let's change the index to n. Like that. There's a lot of n's going on. A lot of raising to the power n going on. So that's going to suggest the root test. Why? Because each term in the series is a simpler term raised to the power n, where n is the index variable of the summation. So taking the nth power of the nth term will vastly simplify it. Okay? So we attempt to find the limit as n goes to infinity of the term from our series, which is raised to the power n, itself raised to the power 1. So these two operations cancel out, raising to the power n and then taking the nth root. They cancel each other out. So this is just the limit of 4 over n as n goes to infinity, which of course is equal to 0. So we have found our L. So this is our L. L is equal to 0 in the statement of the test, so we can draw the conclusion. Okay? So since this limit is 0, series converges by the root test. And we always like to give a clear conclusion or clear summary statement of the conclusion at the end. Okay? So since the limit we got is 0, the root test says that this converges. Okay? Of course, what it doesn't do is tell you what the limit is. That, in general, is a lot harder problem. I mean, you can approximate the limit. Since we know it's convergent, you can get approximations to the limit by just examining the partial sums. Okay? Calculating the partial sums, and maybe you'll notice if you're looking at the floating point expansion or the decimal expansion of the partial sum, eventually you'll probably notice that the first few decimal places aren't changing anymore. It's only the later ones that are changing, so you probably get pretty confident that your approximation is accurate to that number of decimal places. So, but getting some kind of exact evaluation of the limit is a harder kind of problem. Okay, let's look at another example. So this time we're going to consider sum from m equals 1 to infinity of minus 1 to the m, 1 over the square root of m. And again, this test is kind of screaming out the name of the test to apply to it, because it's an alternating series. Okay? The terms of the series are this positive bit here, 1 over root m, and then it's got an alternating positive and negative sign. Okay? So this is clearly a case for the alternating series test. The alternating series test. So what do we do there? We examine the limit as n goes to infinity of just the absolute value of the terms. We forget the alternating positive and minus sign. Well, the limit as n goes to infinity of 1 over the square root of n is 0. Okay? The square root of n is increasing without any upper bound, so the reciprocal of it, 1 over it, is going to be decreasing towards 0. Okay? Getting closer and closer. Okay? So the conclusion, so by this test, this series is convergent. However, note that the series of absolute values, if you drop the alternating positive and negative sign, that series is divergent. If you don't have the alternating positive and negative sign, then the series is divergent. Why is that? Well, so we've already covered this case because this would be a hypergeometric series, sorry, hyperharmonic series. As this series is, second series is hyperharmonic. Okay, we were able to settle all of those by applying the integral test we did last time. Sum of 1 over m to the p, with p equals half. Conclusion was that p was strictly less than or equal to 1, then the hyperharmonic series diverged. Okay, let's go for another example. Now you can tell which test we're going to use for this because we'll use the test we haven't used yet. Ratio test. So this is a candidate for the ratio test. But there's another reason why we recognize, just apart from the fact I haven't given you an example of the ratio test yet, there's a more meaningful reason why we might try using the ratio test. And this is because of the powers of a quantity here, where the power is a function of the index variable n. Okay? So notice that the term features exponents involving n. Okay, so where n or something closely related to it, n or some simple function of it is appearing in the exponent in the term. And these often simplify, let's say, these often simplify when taking ratios of successive terms. Successive terms just means one term divided by the one that came before it, or the one that came afterwards. So let's look at, so this is our AM. This whole thing is our AM. So let's look at the limit as n goes to infinity of an plus 1 over an. The ratio of successive terms. So I keep changing my index variable. An. So let's look at this limit. Okay, so I'm using m as the index here, so this will be m plus 1 over 3 to the power m. That's the an plus 1. Let's take the limit of it as well. And I'm dividing it by an. So dividing it by an is the same as multiplying it by the reciprocal of an. Okay, so I'm taking this limit. Now I don't take that limit straight away. I first concentrate on simplifying this, simplifying the argument here as much as possible. Because I've got a ratio of closely related powers, a lot of those are going to cancel. Okay? So all these 3's at the top cancel with all these 3's on the bottom, and there's one more 3 left in the bottom. Okay? So there's a factor of a third comes out there. Then you've got n plus 1 over n. But that can be rewritten as 1 plus 1 over n. And when we see it written like that, it's clear what the limit is going to be. Okay, so we can apply our algebra of limits theorem for sequences. This is a linear combination of convergent sequences. Got constant term, and then this 1 over n term, which is converging to 0 as n goes to infinity. Okay? So the limit of this sequence we can evaluate as just being a third. Okay? By the algebra of limits theorem. Sequences. And the fact that 1 over n converges to 0, n goes to infinity. So this is our L. We've succeeded in calculating the limit of the ratio of consecutive terms. So this is our L. So you can say, I mean, here I'm just repeating the justification for the test. So eventually, an plus 1 is approximately 1/3 of an. Okay, so that, if it did behave exactly like this would be a geometric series. And because the ratio of successive terms is less than 1, it's convergent. Now, it's only approximate behavior, but then using the comparison test, we get the same conclusion about convergence. So the sum of an is convergent by the ratio system. And one of the reasons I kind of just quickly go through the justification of it again is to, well, just make sure I'm doing it correctly, because I mean, if you just try and learn all these things off by heart, you know, try and memorize all the tests superficially, I mean, the danger is, of course, when you sit down and try a particular problem in a test situation where you can't necessarily look up the tests, although in the exams and class tests we do give you a handout which does have a statement of all these tests. So you're not expected to memorize them necessarily. But memorizing them superficially isn't the best idea, because, well, I know if I tried to memorize something superficially, I could easily sit down and start looking at, see, I remember the limit of the ratio of successive terms, but do you divide the term by the previous one, or do you divide a term by the next one? So do you look at am plus 1 over am, or am over am plus 1? So there's a potential to misremember that. Okay? But if you go through this explanation then, so you get the limit of the ratio as a third, so then you cross-multiply. So this is saying each term in the series is approximately a third times the previous term. Well then, and I remember that it's linked to the behavior of the geometric series. So think back to how geometric series behaved. Yeah, if that common ratio is less than 1, that means the terms are shrinking exponentially. So they're getting small fast enough, so it's going to be convergent. Whereas if this limit is bigger than 1, then the associated geometric series, the terms are increasing exponentially. So, well, if you've got increasing terms, it's automatically going to be a divergent series. And making that link again back to the geometric series test, that also means you can also operate this test by looking at the limit the other way. Okay. So if I did, equivalently, we could proceed by looking at the limit as n goes to infinity of am over am plus 1. Now, in the same way, we find that that's equal to 3. Now, if you've memorized it superficially, you'd say, well, here's my L equal 3. 3 is bigger than 1, therefore it's divergent. But of course, if you link it back to the behavior of the geometric series, then you won't make that mistake. Because you'll say, okay, this ratio is approximately 3, so that means that am is approximately 3 times am plus 1, which means that each new term in the series is approximately a third times the previous term. So you link it back to the behavior of the geometric series test, so you see the approximate behavior of the corresponding geometric series. So you got a common ratio less than 1, so the terms of this geometric series are going to be decreasing exponentially and reach the same conclusion. But the standard or the canonical way or the conventional way to apply the ratio test is not to look at this limit, but to look at the limit of am plus 1 over am, like we did first time. Okay? Just before we end, just one last example. The presence of factorials also suggests the ratio test, because factorials also tend to simplify when you form ratios of closely related factorials. So if we looked at the sum of n factorial over 3 to the power n, well here, if you looked at the ratio of am plus 1 over am, this is our sum of am. So here you're looking at the limit where you've got n plus 1 factorial over 3 to the m plus 1. Then dividing it by am is 3 to the m over m factorial. Now, again, the powers simplify to leave you with a third. And the factorials simplify. All the factors in this product here, n times n minus 1 times n minus 2 and so on, they are all present in the top. So they all cancel out, and you're left with the one factor of n plus 1 in the top. So you're taking the limit of a third of n plus 1. That doesn't have a limit, okay? So a third of n plus 1 is increasing without any effect, okay? Which does not exist, this limit. Or you can say, informally, the limit is infinity. because it's getting larger and larger without any upper bound. And so by the ratio test, this is divergent. The sum of n factorial over 3 to the power n then is divergent. Okay, so the presence of the index variable in the exponent or the presence of factorials, they often suggest that the ratio test will be applicable. Okay? Because both of those operations, factorial and exponents with something to do with n, they have the tendency to simplify when you look at ratios of closely related terms. Okay, so I'll be seeing you again tomorrow. We'll look at more examples and finish off this chapter on series. Okay?